I love action items. That's my go-to because I love content that gives me something to take away and say, "Oh, I'm gonna go put that into practice." So when I build content, the idea is like, what can I be advised to go do? So through this process, I kind of threw this together for this presentation, but it's like it's full of action items. And so we're going to get started with action items telling you guys what you should do from start to finish. And we're going to talk about all the problems that me and Ben discussed about what can we do here? What can we do different? Can we get a win-win somewhere? And we hope you enjoy it. So we're going to jump right into it. So here's the first thing you should do if your homeowner decides they want to put a heat pump in, or you talk them into a heat pump. Even if they have a heat pump, let's say you're going into a deep retrofit, right? Big change out, may have to change some duct work. What are you going to do? And the first thing you got to do is an audit, right? And what is an audit? So we need to jump into what an audit is. And Ben Reed, I believe you got that video I sent you. Can you cue that up for us? I may have to pull the slide deck down. There we go. All right. So, Ben, why don't you tell them what's happening right now from someone at CHP?
Yeah, so this is a new addition to our audit process. We're using a LiDAR scanning app to just go through the home and capture all the rooms and generate a floor plan. You can see it being generated there on the bottom of the screen. Actually, I'm a little bit in the way, but you get the idea. What it does is it saves us a lot of time from measuring all the rooms, and it just spits out a floor plan. We can also go back in and take measurements if we need to of the inside, but it's just a really nice way to get a floor plan quickly. And then we'll take that floor plan and we'll import it into our load calculation software and use that as the basis. It's got dimensions on it, and it really gets things off to a pretty quick start, and really saves some return visits because we can go back into the 3D model and look around and maybe pick up on some things we forgot to look at the first time through.
Yep. Awesome. Well said, Ben. So let me jump back to the presentation. Ben, if you could pull that down, thank you. All right. So what you've seen in there was someone basically using technology to scan, get me a floor plan, right? So I didn't have to go to the job, but here's what that auditor is going to have to do. They're going to have to determine R values of the walls. They're going to have to determine U values, solar heat gain coefficients of the windows, give me good estimates there. They're going to have to run a blower door and give me a leakage target that I can enter into the load. But once I get that information, right, my next move, my action item number 2 is to produce a load calculation from the audit, right? And just to show you how I did that with technology, there's that floor plan, right, from the software. So somebody with CHP sent me that floor plan, and then I took that floor plan and I just uploaded it into my software. Now you'll notice in this picture that that light blue skin underneath the house, you're seeing the floor plan from that drawing. And I literally just erected a 3D model house above it, right? Which is producing my loads. So that's pretty cool. But here's where it gets into the secret sauce, right? So like the program also is going to generate a manual J set of numbers, right? We've got our heating load, which is about 34,000 BTUs. We've got our sensible load, our cooling load, which we're going to dive deep into. But one thing I want to point out is like the house's sensible heat ratio is 0.81, right? So that's an important number to kind of pay attention to. There's a reason for that. So after the manual J, we're going to call this action item number 3. This is where we got to pick a piece of equipment. This is the manual S, right? This is the next step in your action items. So rather than drop a whole bunch of stuff at you, I just kind of threw out on the page what I'm paying attention to when I go equipment searching. And so the cooling tonnage at peak load that this equipment is capable of is 24,000 BTUs, which is more capacity than what's on the load count, right? Because we're at 20,771, right? So we've got some airflow options. We've got available static pressure that the equipment can produce. But look at the sensible heat factor of the evaporator on this unit. It's at 0.78. That's a huge win, right? Where that means we can remove more moisture than the home is producing with moisture at peak load, because the house is at 0.81 and the coil is at 0.78, right? You always want the coil to come in lower than the house. That lets you know you can remove more moisture than the house is producing. That's a big factor. Now, you'll notice heating tonnage on this equipment I have labeled as 23,000. So we don't meet the heating load with the equipment at design. So we have electric resistance that got added. Now, this was a big debate between me and Ben, and this is something you should listen to. So Ben, let's take a minute and just dive deep, right?
Sure.
We thought about going up to the 2.5 ton, right? Because the heating capacity of this piece of equipment was going to go way up. And we were like, man, we could probably cover the entire heating load with a heat pump. But the sensible heat factor of the 2.5 ton was running about, I think, 0.83. So our water removal capacity was not going to be as good with that 2.5 ton. Plus the extra capacity meant our run times are going to be shorter. So it wasn't going to be the best fit for summertime operation, but it was going to be an awesome fit for wintertime operation, right? So we had to make a tough decision here, right? So we went with the aggressive tonnage of air conditioner because we want longest run times we could get in the summertime to deliver comfort. So that was the big decision to go with the 2 ton. And that there's a little bit more to it than that, but
yeah, something to look at when you're looking at variable speed equipment and sizing to a cooling load, especially in a climate like a mixed humid climate like Virginia, or a humid climate, anywhere where it's critical that you control moisture. Look at the minimum capacity. So how far, what's its turn down ratio? What's the minimum? And when we went from like 2.5 tons to 2 tons, there was a big jump in the turn down ratio. Essentially, if we had the 2.5 ton system, then it just would cycle off and on a lot. It wouldn't really get the full benefit of the variable speed compressor.
Yeah. So let's catch questions at the end, if we don't mind. All right. So we're going to keep going. Let's go to manual T. So this gets a little dicey. We're at action item number 4. All right. And here's what I'll tell you. This house had a 3 ton unit in it. There's some major home performance upgrades that are going down, and CHP's process, when they delivered the info to me to run the load calculation, I had to build a load based on what to expect, not what is, right? And the unit there was a 3 ton. So, you start at that point thinking, okay, I'm going to lose some airflow for sure, which is a good thing. I mean, that allows my ductwork to be under less resistance to the blower.
Right.
But what comes with that? Well, if you're looking at manual T and you want good throw and your airflow is about to get reduced, well, then there's a lot you got to think about, because you don't want air just putt-putting out of the grills. So I'm just going to kind of dive into manual T a little bit, and then we're going to jump into manual D. But there's a reason I put this up there first. So we removed some duct runs from this house, right? And there's a reason we did that, right? So I can move more. If I have 2 grills, and what I'm showcasing here is I had 2 ducts going into the master suite, right? And I split that airflow in half in the design software because that's what was there. But when I do the equipment selection and I go back to the program, it shows my airflow, and then the program will leave it like that if I let it, right? It doesn't tell me to do this. But then if I start looking at the amount of airflow out of a grill, I'm thinking, man, that's not a lot of airflow. Like if I'm doing my grill research and I'm looking at throw, I've got no throw. My program isn't going to tell me that. right? So that's where we have to, as a designer, stop and say, if I cut one of these ducts out and I just use one duct to run to one grill, I'll get all that airflow out of one grill. I could size my duct differently,
Mhm.
but I can get more throw out of that one register and get better air mixing through manual T. So a lot of that was done on this project.
Yeah,
So
and something else to add to that is a lot of it gets challenging with existing construction because you're given boot sizes, and you're given registers even, and you can decide, like, is it worth it to change out the register? Maybe. Is it worth it to change out the boot to downsize it? Probably not. It's cut through a hardwood floor. Like, what are you going to do with the extra area? That can start to get expensive. So the other aspect is variable speed equipment, because these flows, this 81 CFM down there, that's at max blower. But with variable speed equipment that's sized correctly, you're rarely going to be at max blower speed. You're going to be somewhere below that. Well, now your throw is even worse. And the original installer maybe didn't do a manual T, so they've got already an oversized supply register that's like dual deflection or worse, multi deflection, and you have like no throw. So when we
mhm,
went and looked at this, it was like, oh, well, that size register, if we combine the total airflow in the room, the throw is actually good. It's not too much resistance. It's not too much noise. Let's delete one of those duct runs and just turn that supply boot into and grill into a passive transfer to the enclosed crawl space now,
yeah.
and it's a win-win.
Yeah, that's where I'm glad you went there, Ben, about the win-win, because we have an encapsulated crawl that was happening on this house. So if we can, one, we're doing less work, right? We don't have to run the extra duct work, and it's like you're actually losing if you do, right? So we do less work for more gain,
Yeah.
and we get the transfer grill to the crawl that's going to be sealed. So
So
that's
we
why
did
we
that
wanted to
on
kind of,
what, four duct
I
runs we
yeah, I believe
deleted?
4 duct runs were totally eliminated from what
Yeah.
was existing, right? And so just to kind of go to the next slide. Oh, why is that not working? Give me a second. There we go. So action item 5 is kind of like 5 and 4 together, really. I mean, it's circular logic. You may have to do, action item 5, go back to 4, back to 5, you dance back and forth, right? So this is kind of the layout. I'm going to talk about this layout a little bit. So when I went there and there was a 3-ton, I ran a true flow report on this existing system. You'll see it has a massive amount of square trunk line underneath the house, right? And, I don't know anything about the job. I get there, the system's sitting on a floor on a couple bricks. It's a terrible looking install. And there was an electronic air cleaner that was right next to the back of the blower. And duct leakage was like super bad. We were talking like way over 400, right? So what I wanted to know is, because this is a weatherization project, we're trying to save money where we can. It's like that's a lot of square duct, and I don't want to replace it all if I don't have to. So I ran a true flow right from the back of the unit, and I captured supply static when I did that, and I think I got around 1100 CFM with a supply static of like 0.1, which told me, well, if I know I'm going to reduce my flow, I know I'm going to reduce my static, and my ductwork's in an encapsulated crawl that's going to basically be conditioned. So I don't have to worry about duct sweating, which means the supply trunk can stay, right? So it's a win-win. Now, when I was sent to this project, I'm working with a company over there that CHP subcontracted to. I don't know these guys, and they turned out to be really good. But you could imagine the fear of going out of town and then pulling off a project that you designed without your own tool bag. It's scary, right? So I was trying to make things easy as possible. So the original install was basically all 6-inch duct. And I said, you know what? I'm just going to leave it all 6-inch duct, because here's the deal. I can add balancing dampers and I can balance my way to victory. I've seen designs where people will get pretty particular, where they have a 6 and a 5 and maybe a 5 over here and a 4, and they let the program drive them so bananas, I guess, to try to like optimize, you know as perfect as they can. So I went into the program that did that initially, and I overwrote that part of the program, and I turned all those fives to sixes because I don't care if my ductwork's a little bit bigger. It's in the encapsulated crawl. My starting collars are already there, right? My boots are sized as sixes. Like, why am I gonna beat that up, right? Because the grill is going to determine my throw. How I get the airflow to the grill is my choice. And I want to do that with the least amount of resistance as possible. And if I've got dampers in the trunk, I can balance the system out. So will I have to balance a little bit? Yeah. But I'm going into an install where I tell my whole team, hey, basically everything's a 6-inch duct. So, if you imagine when you're ordering material, right? If you're underneath in a crawl space and you're just running duct, the last thing you want is people going, hey, what's this duct run? Is it a 5 or a 6, right? You don't want to be having those, discrepancies when you're down in the crawl 90 miles an hour. No, you just want to roll. So it's not going to hurt anything to make all those ducts the same sizes. They're close enough. So that's one little thing as a designer I was thinking about trying to make it easy on the team, right? So it's something to think about. So that's our action item for what I'm calling like I guess what we just showed is that's a good way to play the game, right? Like there's nothing wrong with it. For years, what you just seen, I've did a lot of designs that way, right? And it's just the ACA manuals. Boom, boom, boom. They're in order. Now, Ben's going to blow your mind going a little further on this job. So we're going to kick it up a notch and we're going to talk about how we make a good design a great design. Right, so there's more to it. Ben, I'm gonna let you take it away.
Sure. So Chris sent me his manual J, and I looked over it, and I had some concern about handling moisture. I grew up in this climate. I know when you start eliminating sensible heat load from your building and you don't do anything to lower the moisture, the latent heat load, then it becomes difficult for equipment to deliver the full effect that you need, which is to cool the temperature down and remove enough moisture that your relative humidity can be, ideally somewhere in the ballpark of 50% in the summer. Obviously 55% is fine. You don't want to be creeping up, closer to 60% or above. It's uncomfortable. It's unhealthy. A lot of allergens come into play there. You start to risk mold growth and all kinds of things. So we really want to control humidity. Well, the problem is that Manual J is about controlling sensible temperature, right? I mean, that's what a thermostat is reading, and really controlling the equipment over is the sensible temperature. Well, for the most part, Manual J is looking for it's telling you what is the peak cooling load in the hottest part of the summer and the peak heating load in the coldest part of the winter. They're called the 1% and 99% design conditions. Well, at the cooling design conditions, it's hot. That heat pump, if it's sized right, is going to run all day. It's just not going to turn off. That's what you want. And you're going to have a wet coil. It's going to be dripping water all day long. You're going to put gallons of water outside. The problem is there's another time of the summer that is worse than peak cooling, than the hottest time. That's peak dehumidification condition. So that's where we need a manual that is missing, the manual M. That's the moisture control manual. So I know manual LLH, low load home, touches on this, but I think we need a manual that focuses on, does your equipment meet the load in at peak dehumidification conditions or peak dew point conditions. That's when it's really not as hot outside as it is in the hottest part of the summer, but it's very humid. I'm sure we've all experienced that. It might be, it might be 75 degrees outside and pouring down rain for a week. You don't need to run your AC. You don't need to run heat. But you need to remove gallons and gallons of water. Um, so, uh, so yeah,
So,
we'll touch on
so
what we
Ben,
did
let's,
to calculate this.
yeah, go ahead. Take them down. We'll take them here.
So this is the ASHRAE Fundamentals Handbook, and you'll see it's a lot of numbers, but you'll see heating dB. That's in the first table there. It starts with the coldest month, and that shows you your 99% heating design temperature. So for Blacksburg, Virginia, that's 15.7 degrees Fahrenheit. That's what we're designing the heat pump to be able to deliver all the heat for the house at that temperature. Now in the summer, the 1% cooling temperature is 86.3 degrees. So we want the air conditioner to deliver the full capacity to meet the load at 86.3. Well, we can handle humidity there fine because the system's running a lot. Well, if you look down at the lowest table there, the last table, it says dehumidification. The 1% design condition for dehumidification has a dew point of 72.3 degrees. So if let's say you cool your home to 70 degrees and you open a window and 72-degree dew point air comes in that window, guess what it's going to do? It's going to condense on all the surfaces in the house because the house is colder than that dew point. That's very, very wet air. And if you are ventilating, you're bringing in a lot of wet air all the time. But guess what temperature it is outside for the most part during these conditions? The MCDB, mean coincident dry bulb temperature, is 77.8 degrees. So we've designed our air conditioner to deliver all the cooling capacity at what was that, 86 degrees, but now we're down at 78 degrees. We don't need that much cooling. Our AC isn't running all day, it's cycling off. Well, if we don't get enough runtime, our coil doesn't get wet enough to start dripping water soon enough. We're only dripping water and starting to drain it, and then it shuts off. We haven't removed much moisture at all. We've just lowered the sensible temperature, and by not removing moisture, we've actually increased the relative humidity. So we need to pay attention to this dehumidification design conditions because we need to be able to handle the moisture under those conditions.
And this goes back to Ben, why we selected the 2-ton and when Ben was talking about minimum capacity. So the inverter we chose has an established minimum capacity, which I think was 13,000 BTUs. So essentially what we're trying to do is get that system to run as much as we can. As basically we want it to run through the dehumidification dew point days if we can. Mm-hmm. But to be honest, it's probably not, right? It can only do so much.
Yeah, that was the thing. So, that's why I was really concerned about the 2.5-ton system. Yes, it covers the full heating load. We wouldn't even need electric resistance heat in Blacksburg, and it gets down to 4. I've seen 4 degrees in Blacksburg, and that'd be no problem. We could deliver that with the heat pump and no backup heat.
So,
but with that 2.5-ton, yeah, you're right. It was like 13,000 BTUs was the minimum. It's like can't even go down to 1-ton output. Well, yeah. Our load at the dehumidification design conditions were below that. They were like right at 1 ton. Well, that means that when we need to remove the most moisture, our system is cycling off. We do not want that. With variable speed equipment, we want it running all day on a peak dew point day so that it can remove all that extra water, even though it has less total cooling to do.
Yep. So that brought us to the second design of this job. And I'm just going to talk through this design a little
Mhm.
bit to show how we went from good design to great design. So CHP requires that their jobs meet 62.2 for ventilation. So we chose an ERV, right? That's the way we're handling our ventilation strategy. Well, there's going to be times where the ERV doesn't quite potentially, it's not going to handle our moisture problem, right? So we added a dehumidifier down in the crawl. Now we have all these open grills, remember, from manual T, right? We got all these perfect transfer grills in the floor. So, and I'll be honest, this is a new one for me that we're case studying, and we're going to test this theory. But we're thinking that we're going to sync up, right? The house and the crawl are going to sync together because there's a lot of like ways that air can move between those spaces. And so the dehumidifier install was super easy. So I want to talk about the design a little bit. This is where, you know, if you take the time to put a little bit more thought behind how you're going to lay out the equipment, where's it going to go, what's my filtration strategy, you can really make a design and the maintenance of the design be less expensive than actual standard filters. And so I was pretty happy the way this came out. So I have an ERV that's doing a return to return strategy. And because it's return to return strategy and my main filter, which is one of those large April layers that slides in with super, super low pressure drop, it's based over here in the top where the return comes down. The reason I did it like that is because that eliminates the exhaust filter that's going to the ERV. We all know the ERV has those filters in the core that are probably hard to order. They're probably expensive. So I yanked them out, right? So I've got the main air conditioner filter that's super large, super low pressure drop. And I'm also going to let it be the filter for the exhaust on the ERV. So it's a 2-for-1 move. That filter will definitely probably last a whole year for both of those use cases, right? Now I have a fresh air filter box that I've installed for the intake of the ERV, and I've oversized it greatly. It should last a year. And then the Santa Fe dehumidifier, we don't expect it to run that much, right? It's there as like a safety precaution based on the dew point. So, it's got a filter. It'll probably last all year, right? So the idea is the homeowner may change 3 filters once a year, right? That's going to be cheaper than if they were to change a filter every month. And so just a little bit of like taking the time to say, where can the equipment be mounted? How can I optimize my filtration strategy? All 3 of those filters are MERV 13, you
Yeah.
know, super awesome.
And another benefit of that, when you can oversize a filter, like a nice high quality MERV 13 filter, it gains you so much benefit. You mentioned keeping equipment clean. I used to work for John Semmelhack, and he put MERV 13 on his equipment, soon after installing it, and takes pictures every few years inside the return ductwork that he can see the back of his air handler with the blower, and just shiny metal. Like when he first put MERV 13 on, there's like a tiny bit of dust inside the return duct, and he had like wiped his fingers through it. And then like 5 years later, you can still see his finger marks in the little bit of like construction dust that settled in the return, because no more dust can get in there, in any meaningful amount when it's going through taped or gasketed MERV 13. The other thing is, it makes a big difference on indoor air quality. MERV 13 is where you start grabbing PM 2.5 in meaningful amounts. And PM 2.5 is the most harmful air pollutant to human health. It's fine particles that go deep in the lungs. Some of them are so fine they just pass straight into the bloodstream with no defenses that our body can mount against them. They just go right in. So MERV 13 is when you start, getting like 80% of those out of the air in the first pass. Things like viruses, smoke particles, things like that.
Yeah.
But another benefit of taking a filter and just increasing the surface area is that the air going through it slows down. The resistance drops by an order of magnitude. And now, if nobody's perfect, sometimes a filter in the crawl space gets forgotten about for a little bit. If these aren't perfectly maintained, it's not like you're going to freeze up a coil and damage equipment. Like if they didn't change one of these filters for a year and a half, even 2 years, their equipment is going to be okay. They might lose a little bit of capacity, but they're going to be okay. So we're building in this resiliency in the equipment to less than ideal maintenance.
Yeah, and I will say, like, I wanted all the filters to be it together, because I knew if I had to put the filter in the return air grill in the house, it would probably get changed. But the other ones would have been forgotten about. Right? So, like, I purposely put it down in the crawl. Well, the crawl, when it gets finished, is going to be super nice. We're talking red carpet tour going down there, right? It literally will be carpeted up to the air conditioner. So, and then at some point you have to sacrifice. And I sacrifice putting the filters down there. But if I can go a whole year, the homeowner could literally have the maintenance technician change the filters while he's there. I mean, someone comes to your house once a year, you could have them do it. So it's something that could be pawned off to the maintenance technician. So that's why I was kind of okay with it.
And they really are cheaper. Like it's not just like, oh yeah, it's like, oh, you do it less often, you pay more for, like some of these filters are actually cheaper. So
Yeah.
A lot of the ERVs that we use, they have an option for a MERV 13 filter. It's tiny, it's like this big, it's an inch thick, and it lasts like a couple months. It's $30 a filter. We're using a 10 by 20 MERV 13 that's less than $10 and it's for 6 months to a year. Like that's cheap.
So
it pays off
yeah.
to, the filter box. We spend $100 on an inline filter box to handle the incoming air from outside, but it pays for itself in like a year
First
or
year.
two. Yeah.
Yeah. Yep. So we the idea behind CHP is a lot of questions I was asked was, hey, let's keep the maintenance costs down. So, all right. So I'm jumping ahead. Let's see. So here's where we're going to get to the meat and potatoes of what I want to say. If you don't commission the system, then there was no point of any of it. Like all that work goes down the drain if you don't deliver the capacity where it needs to go. And so this is where we're going to talk about basically standard 310. We don't have to talk about design review because that was the whole design process, right? But now we're talking about total duct leakage, right? This job had major total duct leakage. We've tightened it up. It's definitely tighter now. That was part of the process, right? But this is when you want to check the blower flow, right? You want to set the airflow on the machine, check the watts, make sure everything's working fine. And then, of course, check and charge. So, we believe that's a solid process to polish off all of that design work. Because if you miss one of the marks and it's not working right, well, then you don't know. And
actually, Chris, can I go on a rant about manual M some more? So when you do a manual J and you've got your total cooling load in our climate that's humid, you have to design to the cooling load, because if you like we were tempted to do, try to design to the heating load and try to do it without any electric resistance heat, it hurts you often on the cooling load. And this is a special piece of equipment that we use. This is a cold climate heat pump with flash injection that When it gets really cold outside, that thing just works harder. And because of that, the heating capacity of this heat pump is much, much greater than its cooling capacity, which is fantastic for our climate because we can design to the cooling load and still get most of the heating load covered by the heat pump at much higher efficiency. But let me just throw out some numbers there just so you get an idea of what kind of effect different things have on a design. So when we did the manual J, it gives us a total cooling load and a breakdown of latent cooling and sensible cooling, but it doesn't really give us the whole picture. And a lot of manual J software can, but it's challenging to find all the inputs and get them right. Like what's the ERV's recovery efficiency and things like that. Fortunately, I've worked with people like John Semmelhack and other really smart people who have created spreadsheets with calculators. It's just math, but it helps to have a spreadsheet with the math already there so you can just key in some numbers. Another great tool is a moisture app that Anthony Cox created. And with those tools, I was able to look at, okay, what are all the sources of water coming into this home? One is the internal gains. That's the people living in the home, taking showers, cooking spaghetti, mopping, whatever, breathing. There's like a standard amount of moisture that's generated by human activity in a home. So that's a pretty standard thing. For this home, that was 4.5 gallons of water a day that get evaporated into the air and need to be removed by the cooling system and or dehumidifier. Okay, so 4.5 gallons. Air infiltration for this house, 5.8 gallons of water coming in from air leakage. Now this is during peak dew point conditions. So this is when it's super humid outside. So any air that comes in brings in a lot of water with it. So we also are adding ventilation to this home because when we air seal it, we need to make sure it's ventilated. Well, for this home, we calculated it needed about 92 CFM continuous of ventilation air because there's 6 people in the house. And that's 10 gallons of water a day coming in just from the ventilation air. So, I think there's a lot of misunderstanding about ERVs. I hear a lot of, oh, should we do an ERV or a dehumidifier? Like they're the same. Now, ERVs can remove a significant amount of water in the summer, but they are not dehumidifiers. An ERV in the summer adds water to the space. It just adds less water than straight outdoor air. So in this case, we picked an ERV and we said, okay, what's that going to do to our moisture load? And what it did was take 4 gallons of water out of the ventilation air every day on a peak dew point day. That's very significant. That was helpful in allowing us to be comfortably within the 2-ton capacity range for that heat pump, even though the manual J didn't show it as clearly as it appears when you run the calculations yourself. But I just thought it's interesting to note that when you add ventilation, you bring in a lot of water with it, and we've seen problems in our climate from improving homes, adding insulation, air sealing, reducing that sensible load, and then adding ventilation and putting, in this case, 10 gallons a day in extra on top of the what was there before. About 10 gallons coming in from internal gains and air leakage before touching this house. Now there's 20 gallons coming in a day on that worst day. Like we're doubling the moisture load and reducing the sensible cooling load, so we don't need to run the AC as much. And that's trouble unless you can calculate how much water is coming in and you know you have the equipment to remove it all. And that's why the dehumidifiers there and the ERV, they both play a role in handling the humidity in this home.
Yep. So Ben, I'm going to go on my rant.
All right, go for it.
So, I'm going to keep mine short. So one thing I wish as an industry we would rally around is, as we're getting into the inverter-based equipment, it's not super transparent from manufacturers how they want the test modes to be ran. I did ride-alongs with a couple mechanics, and I say, hey, can you get that thing up to full speed so we could test it out? They're like, yeah. And then it's like, they do their thing, airflow pops up, but nothing on the screen's talking about compressor speed, and like, is the compressor at 100% capacity? I'm not saying all manufacturers. I'm just saying it seems to be very common that the literature is not super transparent. For example, here we are. I just was looking at this one. It says test run, and it gives you dip switches. There's not even one sentence that says you should have the system turned on or off before you set these dip switches. You should, have the thermostat in this. Nothing whatsoever. We're just literally, here's some dip switches, right? And there's more literature in this manual about megging out the compressor than there is about operating it in test mode, so you can check it out with independent third-party tools to make sure that the refrigerant charge is good while it's running at 100%. It's bad. Like, I'm seeing this a lot, and it's annoying. This is my cry to the industry to say, when are we going to push back and say, give me more? Like, in commercial, there was chaos, and like BachNet was, created to simplify things for the commercial controls industry. And that's because transducers and all these parts were being kind of applied, and it was, heavy hitter technology. We're seeing a lot of those controls in commercial now. We've got variable speed outdoor compressor, outdoor fan, indoor fan, everything's communicating. But when are we going to get a protocol that manufacturers are going to stick to that says, hey, that you've got 30 minutes. And you know what? I understand that they all do things a little differently. Like, one may do vapor injection to the compressor or whatever. They all have their little different nuances, how they achieve the capacity they want to for these cold climate heat pumps. That's okay. Tell me if the conditions outside aren't right, and say, hey, I will let you do it, but not under these conditions. We have the sensors on the equipment. We could literally say, hey, now's not a good time for this. Come back on a warmer day, right? But when that warmer day happens, give me something super transparent, right? Make it easy for me to lock this thing into full cool for 30 minutes. And I don't mean full cool where I can only know that the fan isn't going to modulate on the indoor unit. I mean full cool where I can tell that the compressor is at 100% capacity for cooling mode and the indoor fan, right? I need to know that stuff. So anyway, that's my rant. I wish it wasn't like the way it is. But anyway, all right. So that's my slide deck. So
yeah, and just like to drive home the point of commissioning. I mean, you mentioned like what's it all for if you don't commission it? Like, if you don't know walking away how well that equipment is working, is it doing what you designed it to do? And it means, not assuming airflow, but actually measuring it. And not just total system airflow, but if you've done a room by room load, like, make sure you're getting the air where it needs to go. You can create a really comfortable home just by doing a good manual J and then making sure the air actually gets delivered there.
Yeah, which would be,
But
getting into standard 221,
right.
which is driven by NCI, like the National Comfort Institute. That's really their standard they drive at ASHRAE, which is where you're doing verification of capacity and airflow to each room. I mean,
Right.
that's super nice, right?
Yeah.
Then you're walking away feeling very comfortable about the install you just laid down.
Yeah.
And with that level, I mean, how do I say this? I feel like there's a part of me that feels like we're talking about this and it's pie in the sky, right? And people are like, the hell with that. I ain't never going to do all that. Like, that was way too much. And I get that. Hell, I probably was that guy for quite a while. It's a stepping stone process. And every time you do one, you learn a little bit more. I mean, I'm gonna be straight up. I learned a lot from Ben on this design right here. Right. I was not super confident to run through the moisture load process. Right. I had to get Ben's help. So I'm still learning. And so like if I hate the fact that like I'm here and it's like, I'm trying to like we're running through the slide deck like I'm tooting my own horn or anything. But no, I'm not. I'm still learning. Like I'm learning from people like Ben. Like Ben's still teaching me stuff. I'm still getting better with my design process. You have to get to that level, you have to just like do it over and over and over and just, pick up little tidbits the whole way. But if you
Yeah.
don't
We
ever
really,
start,
we,
then you're never going to start. You're never going to know any of this stuff. It's hard. You just got to
yeah.
do it.
Nobody's born knowing this stuff, like, I've learned so much from Chris about installation. He has so much hands-on experience with equipment and materials that, I have so many gaps in my knowledge. And the more I can get around people who have even slightly different experiences, but the more the better, the more I'll be able to learn from them. So it's
Yeah, it
like
was
we
a
help each other.
yeah, it
Um,
was a lot of fun. This was a fun project for
yeah,
us.
it was.
Ben, you've got the math part figured out, right? And I've definitely like I love designers who have installed for many years because like that design and that layout and everything, like I know where I want to set the equipment, right? Like because I know how I'd want to access it, how I'd want to maintenance it, right? I know how I want to work the retrofit, and I know like I know if a duct run's probably going to be too far and challenging to run, right? Like if you notice in that install, I knew my ERV duct runs were going to be further. So I made those duct runs increase to 8-inch ducts.
Mhm.
I didn't have to do that, but I thought, I don't know the install team, and I don't know what it's going to be like when we get all that ripped out. Hell, I'm just going to upsize the duct. That way it's not an issue with pressure drop, right? If I upsize the duct, it'll be
Yeah,
fine. And if I have to run an extra 10 feet, it'll be fine. So it's
yeah,
like all these little tidbits from practically installing for years, you start to say, if that's even going to be remotely challenging, I'm just going to make it a bigger duct, right?
yeah.
So a
And
lot of
these
good stuff.
things, like, it really helps. Like, this is the other reason why you commission, is because that's how you learn. That's how you
Yeah,
learn from that's how you find your mistakes, you learn from them, and you get better the next time.
that's right. Yeah.
Like, there's all these rules of thumb and theories and myths that if you design with those, like, you're gonna get into trouble. Like, I hear so many times, like, oh, you don't want your ductwork too big, you'll lose whatever, static pressure or velocity. It's like,
Yeah.
I don't care how low the velocity gets in the duct. The lower
Yeah.
the better. I don't care if you give me a 20-inch duct to a supply grill, as long as I get to size that supply grill to get the throw I want coming out the end. That's all I care. That's the only time I care about high enough velocity, is leaving the supply grill. And if I get
Yeah.
to size that, then I get to choose the velocity there. And I don't care how fast it's going coming up to that point.
Yeah, I hear you. I think some people want to hear what type of technology we were using. I feel like we should probably maybe get into a little bit of that because
Sure,
what I don't want to leave, I'd like people to know if they want to follow that process,
sure.
what we did. Um, Ben, do you want to jump in and
Yeah.
help
So
moderate on
there's
that?
there's quite a bit of there's a few options out there. I started using a 3D scanning app called Matterport. Yeah, it was probably it's been the standard for a while. It was the early app and company. And then we started using Polycam for scans just because it's even easier, and it gives you the options of, if you have a smartphone with LiDAR on it, you can use LiDAR. If you have a smartphone that doesn't have LiDAR, you can still do 3D scans with your camera, and it does the math knowing the perspective of the camera. It still gets a pretty good 3D model that's like fairly dimensionally accurate. And so what these programs will do is give you a 3D model that you can manipulate and kind of like go into like a Google Street View where you can look around. But they'll spit out this floor plan that you can then you can turn it into, I mean, it'll come out as an image. You can make a PDF. And then a lot of the Manual J software options allow you to start with a PDF of a floor plan, which, you know, if you're new construction, you're used to having a floor plan to design off of. If you're in existing construction, you're not used to having a floor plan, because how many homeowners have like a scaled, dimensioned floor plan of their home? Not many, unless it's a fairly new home.
Hey,
So
Ben.
this gives you that. You can put the PDF in RightSoft, in you know, Quick Model 3D, and you can design based on that.
So
Hey, Ben, I want to just pause you for 1 minute. I want to let Shelby jump in here. So Shelby represents Conduit, and they are a LiDAR-based technology that will scan the home and also produce a load calculation. So if this is a perfect time, she hasn't got to talk a lot about that through these webinars. I would love to let her just tell everybody about her product in relation to what you guys just did.
Please, that's a game changer.
I feel like I need to be a beta tester.
I mean,
yeah, me too.
Please shoot me a message after this. But well, thank you, Jeremy. That is exactly what we do. And that's the part that we want to streamline. So we use the same core technology that Ben's been using for years. LiDAR, it's only been available in the market since about 2020, but it's in Apple devices like iPad Pros and iPhone Pros. And you can use that to scan, just as Ben showed us, scan the home, build out a 3D model, 2D floor plan, but we take the next step so that you don't have to go into another platform. Your job is hard enough. And after watching the last hour, there are so many steps to this. What could we do to streamline? So we actually automatically put that into a load calculation for you. So we pull in property data, we use templates, we use a whole range of different features to sort of streamline that data collection for you, and pop out a load calculation. Our main our target, and one that every user hits, is a load calculation about 15 minutes or less. For about 2,200 square feet. You get that 3D model, you get the 2D floor plan right away, as well as be able to use that with customers as part of your sales process. Because I think one thing that we've seen a lot over the course of this webinar is the more we talk about the different steps that you need to do a given installation, the more people are like, well, that's more time. That's a huge cost. And so for us, our main objective is to help folks be able to use the load calculation, the work that you're already doing, similar to how folks use MeasureQuick to be able to sell software, and to be able to sell the install using the software. And then to see a few questions in the chat. One of them was about Android devices. So Android has not advanced its camera technology as much. They do not use LiDAR in their devices. So Apple has made a play to be able to build out this whole augmented reality ecosystem, and that's why they use LiDAR. It has all these other cool applications like dimension data, which is why this is primarily on Apple devices. We have yet to find an Android one that supports this. So hopefully in the coming years, for those who are loyal to Android, I totally understand. I just went from a PC to a Mac, and it's been an interesting couple weeks. And then the name of the software is Conduit Tech, which now Ben Reed is sharing our website. So check us out. But this, I know you all didn't come to hear this, although I saw Danny Go's note in the chat that he once got architectural plans from a home built in 1926. I would love to see those, because I'm sure those were super interesting. So I am going to pop back off and maybe hand it over for our next question. So our next question was about the implications of the airflow options that are selectable for a Mitsubishi SVZ air handler. They said that they think those speeds are supervised by the sensors in the air handler, but was confused by the implication that the airflow options had.
You're not the only one confused by
Yeah, right.
Mitsubishi's control of their air handlers.
Yeah. So this is where we're also gonna answer like the data is just not super transparent enough. Like we, in their submittal sheet, it shows the 3 flows and it shows one sensible heat ratio number. Okay, where do I go
Doesn't
from
add
there?
up.
Does that mean I can get the same sensible heat ratio at all 3 flows at the same conditions? Because that's what I'm potentially thinking. Is my EEV gonna modulate and make that happen for me? I guess so. This is where we don't have enough data from manufacturers. This ties right into like the startup paperwork that comes with the equipment.
I
And if
will
it's
say
there,
that
it needs to be
in
cleaner.
Mitsubishi's case, they do have Diamond Builder, which is a software that is a selection software, and it gives you a ton more data than the submittal sheets do. I play in the Mitsubishi world quite a bit, so I have all these same pain points that you guys do. But I do
Yeah.
know that if you take the time to use Diamond Builder, you can do a true manual S with Mitsubishi's equipment in Diamond Builder, and it will give you can put in your design temperatures, and it will give you your latent, it'll give you your sensible and everything like that at design, and also some of these other things too, like airflow or sensible heat ratio at selected airflow and stuff like that. So there is a little bit of value to taking their Diamond Builder class if you're going to do a ton of Mitsubishi branded, installations. But to your guys' point, everybody can't be an expert all the time on everything and use every manufacturer's software. So there needs to be some kind of consistency with the way they publish the stuff that's widely available to everyone.
Yeah. I mean, this was my first design with their piece of equipment. Ben kind of was shooting me data. And then at that point, I felt comfortable because I'm looking at the published sensible heat ratio from the submittal. And I'm looking at the sensible heat, sensible heat factor of the coil. And I'm looking at the sensible heat ratio of the house. And I'm like, well, we've got a good number, right? We know this thing can achieve what we're trying to do. How far can I optimize that? That's where I'd like to dig in deeper and know more. But, just like reality, man, I don't have all the time in the world to just go dig and find everything I could possibly want about that equipment. I mean, in the reality, I was playing contractor, and contractor only gets so much time to design a job and move on to the next job. So that's where I'm like, the manufacturers have to be more transparent and pushing data out there and get it to me. That way I can make better decisions faster. And I get it. Maybe they want to be proprietary, and like there is this whole like suck you into their world, right? Like I was a dealer for many years, right? You get sucked into the world, and the more you get tied to the brand, you learn the nuances of the brand. And it makes it harder to go use another brand because you got to get buried into their world before you get access to their portals, or you're calling your friends who are dealers for that brand and say, hey, could I borrow your login so I could look at what I don't have access to? I mean, how many of y'all in the chat have literally had to put in another brand and did the research on it, but then called your buddy and said, hey, could I borrow your login? Because I really like to look at the expanded performance data from this brand, and I don't have a login for it because I'm not a dealer. That's bull crap, dude. Like straight up.
I remember
that's the world we're living in.
I remember back in the beginning of the rights off days, like nowadays, people still complain about the matchup data and the HRI data that's in rights off. But I remember when it was all lock and key proprietary, and the only thing you got was generic data in rights off, and you had to be the dealer to get the release of their information. Like you had to be carrying all that. So I will say that this stuff has came a long way. And I know rights off fought that fight. Like they went to war with these manufacturers to get their data into their software, and that's what it took. And I think it's going to take that again as we move into these other proprietary companies that weren't necessarily part of that.
Yeah. Well, it's just disappointing, Jeremy. That's all I'm going to say, man. It's like,
I agree.
When in life has it ever been fruitful to hold back in any business? You know what I'm saying? Like, the more open you would be, the probably more attraction you would get. The more mechanics and designers are going to embrace your brand if you put the information out there. The more you hold it to your chest, the more people are like, I don't know if I want to mess with that, because their information's hard to get. For me, it's a huge turnoff.
No, I agree. 1,000%. Trust me.
So.
Awesome. So in from the chat, there was a concern about the latent load, and just, I think, an echoing of the sentiment about Ben's concerns. And moisture loads are not consistent with sensible loads and outdoor temps, but a perspective that they don't dramatically change from 80 to 90-degree days. And just, I think there's a desire to speak a little bit more to this point from the chat earlier.
Yeah, and that's true. Like the dew point doesn't change a ton when the temperature swings, by 10, 15, sometimes 20 degrees over the course of a few days. But what happens when your latent load is the same, but your sensible load drops dramatically, is your AC doesn't run as much. And now you're having a harder time getting that water out. Really, if we're talking controls, this is what gets me, is that this equipment, like from Mitsubishi, this Hyperheat variable speed, it's some amazing equipment. The controls, they're not amazing. This equipment could do phenomenal things. It could ramp its blower up in the winter. It could ramp its blower up on a hot day and give you incredible efficiency. But it would need to ramp down when the dew point is high and the sensible cooling load, be able to remove more moisture, sacrifice a little bit of efficiency, and get that water out, and prioritize the water removal. Like, the equipment can do it, but the controls are just dumb, in my opinion. And
to your point too, they also have the sensors that can do it. So it's Mitsubishi and all these guys have all these pluggable sensors that do, they sense humidity and temperature, and some of them sense even other things besides that. So like, all the technology's there. It's just a matter of thinking that way, I think, for them to get the controls to do it.
You're right. 100% of the hardware is there and the software is not. And it's proprietary, so you can't do anything about it. That's frustrating.
Absolutely. Okay. So with that, our next question is from Lopez McFly. Why would I choose an ERV or an HRV? What are the points I should look into to make that decision between those two types of technologies?
Yeah. So in our climate, we're definitely using ERVs because the basic difference is that an HRV has a heat exchange core. It can be like aluminum, okay? You've got two channels of air passing over each other. Let's say in the winter, you're sending warm, stale air outdoors and you're bringing in cold, fresh air indoors. In an HRV, you get to transfer the heat from the stale air going out into the cold air coming in and warm it up almost for free, because all you're doing is driving a few efficient fans that move the air, and the heat exchange happens because because of equilibrium. The heat wants to find cold places. So an ERV adds a vapor permeable core, heat and moisture transfer core, where if it's cold outside and I'm humidifying my air and it's warm and humid enough indoors, but it's cold and very dry outdoors, I get to not only preheat the air coming in from outside, but I get to transfer some moisture into it. And the opposite is true in the summer. If I've dehumidified my air and it's very hot and humid outside, when I bring in fresh air, I get to dump, a good portion, up to half of that heat and humidity, into the stale air going out. So when it comes in, it's not that hot, it's not that humid. And that made a big difference on this project. That cut 10 gallons of water a day coming in to about 5 gallons of water a day coming in through the ventilation system. So you have to look at how does it affect your heating and cooling loads. And for us, it was a no-brainer because it removes so much water that if you were to try to do that with a dehumidifier, it would be very expensive because you're paying to remove it with a dehumidifier, which just converts it into sensible heat, and then you have to pay to run your AC to remove that to the outside, so you're paying twice.
Let me ask you two guys something. Cost being the same, is there ever a reason to put an HRV in when you can put an ERV in? Like, is there a reason where you would choose that over one? Even in a market, say it's not, we're not in too high of a moisture market, climate zone. Like, still, I think the choice is ERV. I, as a designer, don't have a good reason to ever pick HRV over ERV in any given situation.
So there are some cases where you would want an HRV over an ERV. I've never designed in a climate that does, but I think it's more the climates that have a dry summer, so they can get hot. Let's say like Phoenix, maybe, where it's over 100 degrees outside, but it's dry. So you don't really need to transfer that much moisture. You just need to transfer the heat really efficiently, and that's where an HRV can actually be more efficient at transferring sensible heat, because you can use thin aluminum plates that transfer heat like a champ, Sure. Whereas the ERVs, you've got like paper core, and paper's not as great of a thermal conductor as so you make some sacrifices in order to transfer moisture. But in our climate, man, that's where the money is. You want to get that moisture out.
No doubt.
Awesome. Thank you for that. And one of our last few questions is from James Hutchinson. What are the recommendations needed for total duct leakage and blower door fan airflow calculation with MeasureQuick? Do I need to have the 2 separate airflow tools listed earlier, or just one or the other?
That's for you, Chris.
Yeah, I'm reading it again. What are the recommendations needed for total duct leakage and blower fan airflow calculations with MeasureQuick? Do I need to have 2 separate airflow tools listed earlier? Just the one.
So
I don't know if I'm not sure I fully understand
or the enthalpy
question.
Probes, and they're saying like, what do you need to measure airflow? Can you do it with enthalpy probes, or true flow, or how do you do it?
So in MeasureQuick, let me see if I answer the question right. So in MeasureQuick, well, let me back up. If you do the standard 310 process, duct leakage is step 2. There's design review, and then there's total duct leakage. And why would you even progress if you have duct leakage? Because if you have duct leakage, you have a problem, and you should address duct leakage. Once you address duct leakage, then you move on to total system airflow. If you're testing airflow with tons of duct leakage, why? What's the point? It's like essentially you have a broken system. So back up to, if you follow the standard 310, and there's a standard 310 tool you can follow, if you have a significant amount of duct leakage, it'll basically say you're not passing, right? And a lot of people I've talked to, they won't even continue. They'll just go back to the builder and say, hey, you need to address this duct leakage, and I'll come back when you do, and then we'll keep going. And that's how the game should be played. But to dig into that a little bit, you can download the MeasureQuick app, and then the MeasureQuick app will let you activate the digital TrueFlow system, and you can use the TrueFlow inside the MeasureQuick app. It'll activate just like any other tool, right? And then when you activate it, now it's an app sharing tool, not a streaming tool. What that means is, in the app, when you want to use the TrueFlow to measure airflow, you'll click the button. Once it's been activated, you'll see it from the home screen on the gauge screen. You'll say use TrueFlow. What'll happen is MeasureQuick will pause, right? And then you'll hop over to the TEC app, and then you'll run out the TrueFlow test. When you're done, there'll be a button that says return to MeasureQuick. You'll return to MeasureQuick, and then all of that data, your external static pressure, your airflow, all that gets imported back to MeasureQuick as a static measurement. And then you can just keep going down your MeasureQuick process. That's how how that integration works.
I will add this though, just in terms of the question here. So you can't, in terms of 310 and the workflow and what's allowed and not allowed, you can use your duct tester to measure duct leakage, and then also use your duct tester as a pressure matching device and use it to measure airflow. But here's the caveat with that. The duct tester is only going to get you to about 2 tons. And then you're going to have to do something else. So there's no reason to not own the true flow meter. That is the one thing that gets you just about everywhere you need to go when it comes to measuring airflow in the system. There's other methods too, but like the true flow, has the word true in it for a reason, because it's almost always going to give you the true flow of what you're measuring there. So
I'm just going to jump out there and throw this, like if you're following ANSI standards, ANSI has 4 methods they approve, right? Total external static pressure, or external static pressure, whatever you want to call it, right? A true flow, a flow hood, and pressure matching. 3 out of the 4 of those are volumetric airflow. There's probably a reason they were hell bent on that, right? So what I'm trying to get at is, I'm not saying TESP don't do it, right? Like, here's the thing. It's all about barrier of entry. How much money do you have to spend? Because a true flow, it's not $100 tool, right? It's pricey, but it's super accurate. You get what you pay for, right? I mean, if I'm a young technician and I'm trying to afford channel locks, right, am I going to go buy my true flow? Probably not, right? Because it's a next level tool, right? It's for next level people who are wanting to prove out and do high performance contracting. But would I get me a total external static pressure meter? Yeah. Now, this is where I'm going to be a little bit biased, and I would say maybe I'd get me a DG8, because that's like one tool that'll gateway you into the true flow tool later. So it's like, maybe if you can afford a little bit more money for a good manometer that you can use for all kind of stuff, well, that's an awesome point of entry. And then you can use that to check external static pressure. And then you have a way of, like, at least some barrier of entry to start taking that measurement, right? And then you could work your way up to a true flow later. Like that. I'm not,
I would go to say that you should have a manometer of some sort that you can measure static with, no matter what. If you're an HVAC tech and you don't have a manometer on your truck or in your toolkit, then you're doing something wrong, in my personal opinion.
Yeah, and the DG8 is the one I reach for when I'm out in the field, because it's small, it's easy to hook up, it's got magnets on the back, it's a great manometer. But I will say about those airflow measuring methods that, if you are using external static pressure and the manufacturer's airflow chart for their coil, just make sure that your probe placement is correct, that you're actually getting in where you need to measure static pressure, like between the filter and the coil. Like, you don't want to accidentally capture something that reduces static pressure without realizing it. And also, your coil's got to be clean. If you try to do that on a dirty coil, everything's out the window, because that chart was created with a clean coil. So for that to be valid, you've got to have a quite clean coil. And finally, about the flow hoods, people may not realize, but a lot of bolometers or passive airflow hoods are just not very accurate. Because what do? They funnel all the air through a small opening to measure it. But by doing so, they change the airflow, they restrict it. And then they have to do some calculations to be like, well, I slowed it down by measuring it, but I probably only slowed it down by this much, so it was probably that much. Well, a lot of these, you end up with plus or minus 15, 20% error. That's why some people call them random number generators, because you can measure a flow, measure it again, and be 25% off from the measurement you just took. So just be careful with the passive airflow hoods, and if at all possible, I know they're expensive, but invest in good tools. And if you're going to do room by room airflow balancing, and you want to do that to plus or minus 5% or 10%, you need a tool that has better accuracy than that, or you're going to be very frustrated or confident in something that is not right. So if you can use a powered flow hood, it's got a fan in it that compensates for any pressure that it adds to the measurement and gives you very accurate and repeatable results.
Yeah. Residentially, I love the powered flow hood. Like I don't think you should be measuring residential airflow without powered flow hood for a bunch of different reasons, in my personal opinion.
Awesome. Well, on that note, thank you each of you for joining us today for both the incredible presentation and handling all of these rapid fire questions. The chat has been lit up today like it hasn't been before. So thank you to our audience as well for contributing so much to today's direction. The last thing that I'll say is just thank you to everyone who participated today and for sharing the practical knowledge that is really required to be able to do these heat pump installs correctly in the field. So with that, as our final presenter of the day, I'm going to bring on Brent, who will share a little bit about the Heat Pump Summit before handing it over to Ben.
Awesome. How's it going? Awesome. How's it going, everybody? My name is Brent Davidson, and I'm here to tell you about the Heat Pump Summit. The Summit is a conference and training event for contractors. It's on November 13th in Berkeley, California. It does cover both HVAC and water, and there's 3 awesome parts to it. We've got a detailed training day, runs the whole day, detailed conference content, and trade show tables from awesome exhibitors. The training, I can tell you a little bit about that. It covers everything from starting from really end-to-end how to run a business on electrification, moving fully away from gas, and it then goes deeper into system design for heat pumps in particular. That'll be done by a building engineer. He's seen a lot of designs. He's seen a lot of stuff go right, and he's seen a lot of stuff not go right. He's going to correct a lot of understanding about heat pumps, airflow, etc. Then Measure Quick's own Joe Medosh will round it out with commissioning training. Super critical step, as we obviously know. There's also some water heater trainings. Ream will be there, a couple others. And for folks in California, that'll qualify you for a Tech Clean California rebate program. Conference content, check it out on heatpumpsummit.org. A quick overview. I will say it's very focused on contractors, and it'll help you with kind of that higher level knowledge beyond the detailed training. Bunch of strategies for fitting in new electrical load into a home's existing panel, avoiding that panel or service upgrade, stuff like emergency retrofit, installation strategies, and more on demand response and some exciting stuff like that. It's going to be a jam-packed day. Everything's really from that building science-based approach. And the goal of the event is just to have happy heat pump customers, size small for the grid, and really meet other expert contractors who are on their heat pump journey and taking this stuff on. We've got a special discount code for Measure Quick. MQ100 gets $100 off, and it's out in the San Francisco area, but we do have a great hotel rate, $139 at DoubleTree, right on the water. Beautiful place. Like I said, more info at the heatpumpsummit.org, and you can reach me directly at Brent BRENT at heatpumpsummit.org. Thank you very much.
All right, everyone. One last little thing for you is there was some great comments in the stream about controls and about kind of even the open source nature of certain projects that have been successful that we need to see more of in the HVAC world. And I agree. And so regarding kind of controls and diagnostics, on the diagnostic side, we've this recently been announced that Senti Predict is being phased out. So it will be kind of sunset in about 2 months' time. And there's doesn't seem to be anything to replace it, at least for advanced diagnostics. So later this afternoon at 2 p.m. Eastern, myself and Tim DeStasio are just starting a bit of an experiment, a bit of a live stream on the Tealmaker channel. So that's it's my own YouTube channel, but you can kind of join along in the comments. And we're going to be live kind of discussing and gathering requirements for what a diagnostic system should do that, theoretically could feed data back into a system that could confirm the ASHRAE 221 compliance of the system performance. So If you have time, jump into that live stream. But if not, it'll be recorded and you can watch it later. So yeah, and our next live stream for Measure Quick for heat pump commissioning is not scheduled yet, but just kind of pay attention to our various social channels and we'll be announcing it there. So thanks everyone very much, and enjoy the rest of your week and happy Halloween.